In the first two videos, we talked about how to make alcohols, and we said that one of the approaches that we could use was the sodium borohydride reduction of a carbonyl compound, and we also looked at the use of Grignard for its carbonyl compounds as well. But for now, in this section, we want to talk about the reactions that alcohols themselves undergo. You actually had a little bit of this back in Organic 1 when you were discussing things like SN1, SN2, so on and so forth. Well, here we'll just take it a little bit further, and let me just show you some examples of reactions that alcohols themselves can undergo. Alright, look at this note that I have on the top of page 94. It says alkyl halides may be prepared from alcohols, okay, and then I have the higher the order of the alcohol, the greater the reactivity. So this is a really good reaction. Okay, this is a tertiary alcohol. That's the highest order that you can have. And this particular reaction, hopefully you will recognize. Okay, this is a substitution. We're going to have an OH here, and we're going to substitute a chlorine. Okay, do y'all remember what that was called? Right. This is called an SN1 reaction. SN1. So let's go back and take a look at how this all happens. Okay. Now notice on the reaction arrow we have HCl. This is hydrogen chloride, not hydrochloric acid. This is HCl, hydrogen chloride. There's no water involved here other than water byproduct. And the reaction is being conducted in ether because it solubilizes both of these components very well. And it's also being conducted at a relatively low temperature so that we kind of keep control of what's happening here. So the sample problem 17.16, we want to provide a detailed step-by-step mechanism for the above process. Okay? So let's just figure out how this is going to work. Now, the first step, and this is always true anytime you have an alcohol, is going to involve converting a poor leaving group into, you guessed it, a good leaving group. Okay, so all I've done here is I've reproduced the structure of the tertiary alcohol. Now with mechanisms, lone pairs are very integral. We want to show them. Okay, so here's my reaction arrow. And you can show the arrows going one way or both ways. It really doesn't matter. But let me sketch in hydrogen chloride. Now recall that hydrogen chloride is an example of a strong Bronsted-Lowry acid. So what's the first thing that's going to happen? One of the lone pairs of the tertiary alcohol is going to pick up this proton, okay, from HCl. Chloride being very electronegative will take the electrons with it. And so where you formerly had a very poor leaving group, we're going to convert that into a really good leaving group, which is water. Water is an excellent leaving group. But let's show that with all the appropriate curved arrows. So the methyl is here, okay, and now you have a proton, a protonated alcohol, so to speak, there, and you have a counter anion, which is quite stable. As chloride has an octet of electron, it's pretty stable. But this species here is not that stable. So what's the next step? Well, water is a byproduct, and so water is formed at this step simply by breaking away. Water is functioning as what again? A leaving group. Now, we're going to draw equilibrium arrows again. The water, in theory, can come back in and form a bond, but it's more favorable that we get a substitution because the product that we're going to get is more stable than the original product. Okay? But we still have to show all the steps. So here's our methyl group. Okay? Now we have a carbocation, but we also have water. So we've accounted for the byproduct that we show in the preliminary reaction. And chloride is still here. There's chloride. Now, like I said, chloride is pretty stable on its own, but this is a tertiary carbocation. And it would much prefer to have an octet of electrons around it. So any one of the four lone pairs can come in here and form a covalent linkage. And there you have it. Okay, that's how this reaction works. So let me just draw an arrow going straight to there to show you our final product. So as a reminder, this is called what? The overthrow process is known as SN1. Okay, SN1. Substitution, nucleophilic, unimolecular. And the rate determining step was right here. Okay, that's why it's 1. The rate determining step is right here. This is also called the rate determining step, the RDS. And the rate determining step is always the slow step in the reaction. Well, this reaction works pretty well, particularly if you have tertiary alcohols, right? Works okay with secondaries. It doesn't work with primaries. And but you know, HCl is kind of hard to work with because it's a gas. It's very difficult to work with gases, particularly if you want to make a stoichiometric delivery of a particular gas. Easier said than done. So, is there another thing that we can do, say for example, for substituting a halogen for an OH group? And there actually is. Now I have a reminder here, this goes back to chapter 10 in Organic 1. It said primary and secondary halides are best prepared using phosphorus tribromide or thionyl chloride and pyridine. These are advantageous to HCl, which is highly acidic and often results in undesired rearrangements. So without going into much detail, folks, there is a more effective means of replacing an OH, and we're going to look at examples whereby we replace the OH with the bromine. Now, if you use PBr3, okay, it's restricted to primary and secondary alcohols only. You can't use it with tertiaries, all right? So if you have a tertiary alcohol, okay, all bets are off. No reaction with tertiary alcohols. You're going to see in a moment that's because they're hindered and they can't undergo the proper reaction mechanism. Now, as you know, we're not that concerned about stoichiometry in organic chemistry, but sometimes we show it just to get a feel for what's transpiring. Folks, if you have 3 equivalents of alcohol, okay, can be converted by 1 equivalent of PBr3, that's because you're substituting 3 bromines for 3 OHs. So where you formerly have an OH, you're going to end up replacing it with a Br. Okay, so again, this reaction is restricted to primary and secondary. 2-pentanol is an example of a secondary reaction. We'll look at the mechanism on the next page. Is there another means by how to replace, for example, OH with a chlorine? Well, you could use HCl here, but there's another means, and that's the use of thionyl chloride. This is thionyl chloride, and we have pyridine. Pyridine is going to function as both a solvent and as a Lewis base, okay? Because you're going to generate hydrogen chloride as a byproduct, and so therefore you need a Lewis base to absorb that. So pyridine serves 2 roles. This compound on the left is called benzoin. Okay, and you actually made this compound in lab right before the holidays, and it's sitting in your flask in your drawers as we speak. Okay? Oh well, that's another story. But what's happening here? We're going to go from a secondary alcohol, which benzoin is, okay, to a secondary, in this case, alkyl chloride, RX, by using thionyl chloride and pyridine. So the important thing here was to recognize the transformation, and that is you converted the secondary alcohol to a secondary chloride. And this, by the way, is called dansyl chloride. It used to be used in protein chemistry research. And these over here, folks, are your byproducts. Okay? Again, you're not responsible for byproducts, but just be aware of that. There are byproducts. And the reason I place HCl in brackets is because that HCl actually gets absorbed by the pyridine to make what we call pyridinium hydrochloride, which is a salt that's very easy to separate from your organic product. Okay? So these are the 2 reactions in a nutshell. So why don't we do this? Let's take what we've learned there and expand upon it a little bit. I'm going to go to page 95. you'll flip over to page 95 with me, let's take a look at this. Okay, these are the three reactions that we talked about. This is just a summary of what we discussed. You should probably be able to do these by looking back at what we just talked about. Okay. All right. What do we have here on the left? What kind of alcohol is that? Okay, this is called T-butyl alcohol, okay, which is an example of a tertiary alcohol. And what do we say tertiary alcohols undergo? They undergo SN1 reactions with HCl. So this turns out to be relatively simple. Where you formerly had an OH, you now have what? You have a chlorine. And while you're not responsible for the byproduct, I'm going to go ahead and sketch it anyway, HCl. I'm sorry, that's not right. H2O. Okay, that's your byproduct. Okay, now here we have isopropyl alcohol, which is a secondary alcohol, and we're reacting with PBr3. So as you probably know, just identifying the reagent there, that it's a source of bromine. And so where you formerly have an OH, you now have a bromine. Okay. Now the previous page I showed you the stoichiometry. I had 3 equivalents of alcohol for 1 equivalent of that. We're not going to concern ourselves with that. We just want to know the overall result. And similarly, we have a secondary alcohol here. Okay, this is a 2-butanol, and we're reacting with thionyl-chloride and pyridine. And just like the previous case, we're going to substitute the OH for, in this case, for chlorine. So if you stop and think about it, it's really just incumbent upon you to recognize that you have a halogen source as your reactant, and therefore you're going to, okay, this should be a chlorine, right? Cl. All right, that's chlorine. Sorry about that. Cl. But in every case, though, we just replace the OH groups with the halogen that we saw as OH. Here we have an OH, OH replaced with Cl, Br, Cl. Okay? All right. Moving a little fast, but those were simple. And let's try to get an appreciation for how this reaction works. And this will help you understand furthermore why this reaction is limited to primary and secondary alcohols. Okay? So take a look at sample problem 17.18 on page 95. Folks, this is PBr3. Right? There it is, PBr3. And this is something you've never seen before. The question is, who's the nucleophile, who's the electrophile? Well, traditionally, to be a nucleophile, you have to have a lone pair, right? Well, okay, so is oxygen the nucleophile, or is phosphorus the nucleophile? If you look at this closely, you may recall oxygen is more electronegative than phosphorus. And furthermore, look at phosphorus. It has 3 covalently bound bromine nuclei, which makes that phosphorus very electropositive in its core. So here, the oxygen is going to act as a nucleophile, right? So let me draw that curved arrow going like that. And let's go ahead and label these things. This is the what? This is the nucleophile. And this would be what? The electrophile. What's going to happen here? You can tell what's happening by looking at the next set of intermediates. Folks, one of these 3 bromines in the form of bromide is going to break off. Okay? And therefore, we're going to have a negative charge here. And similarly, we're going to end up with what? A positive charge here on the oxygen. Let me just put it right there. Okay? What kind of reaction is that? Who can tell me what kind of reaction this is? Oh, this is an SN2 reaction. Okay, it's SN2. Now, recall that OH, we've said all along, is the poor leaving group. But by virtue of adding all these nuclei to that oxygen, we now have a good leaving group. So OH is the poor leaving group, but all of this, guys, is a very good leaving group. So what's going to happen? Bromide will attack here, and this whole portion of the molecule will break away. Okay? What kind of reaction is that? Once again, it's an SN2 reaction. So this is the first time you've ever seen that. This is two consecutive SN2 reactions, whereby we have a nucleophile reacting with an electrophile, and then the bromide becomes a nucleophile here. And this host species over here would be our electrophile. Now, categorically, what did I just say about that? This is a good leaving group. A good leaving group. Good leaving groups are important. You may remember the good leaving groups are they're basically the conjugate bases of strong acids. All right. So the net result is you have a bromine where you used to have an OH. And folks, see the species here? This can go back and repeat this process 2 more times because there's still 2 bromines remaining. Okay. So this is a very important mechanism. It's one that you should look over just to get an appreciation for all the different features associated with it. Let's look at something kind of like that by flipping over to page 95. You may remember in Organic 1, back in chapter 5, okay, we talked about something called inversion of stereochemistry. And that's what this deals with, okay? Here we're going to convert alcohols into what we call tosylates. And the reason we're doing that is because the OH is a poor leaving group, and something called a tosyl group is a good leaving group. Okay? This goes back to chapter 5. And we also had it in chapter 11. Okay. So let me show you the general reaction, and then we're going to apply it to a real-world system. So what do we have here? This is an alcohol. And what do you know about the OH group? Poor leaving group. That means that nucleophiles that would attack the carbon bearing the OH, it's not going to come off. So what are we going to do? In this case, we're going to replace this proton, okay, with this whole group. Right, this whole group here. Now this is called paratoluene sulfonyl chloride, okay, and we abbreviate that just by writing the letters TOS, okay, TOS CO, or tosyl chloride. Now you got to have pyridine around because it's going to soak up the acid that you produce as a byproduct. And it's also going to function as a base. So that's why we get pyridinium hydrochloride as a byproduct. So the OH here, okay, is a poor leaving group. I'm just going to abbreviate it LG. But the whole tosyl ion, this whole thing, okay, is a good leaving group. Alright. And so therefore, if you have a nucleophile, the nucleophile can attack here, this whole system will break off. But all the rules that apply to SN2 are in vogue. So not only are we going to get a leaving group departing, we're also going to get inversion of stereochemistry about that center. So let's take a look at that. So how do you carry out the following transformation? In other words, going from A for this alcohol to B, which is a cyano compound. Now ultimately this is how we can make ibuprofen. And let's talk about that, because it involves the chemistry that we just discussed at the top of page 96. First off, what kind of alcohol is this in terms of its order? Folks, this is a secondary alcohol. Now, why is that important? Because you couldn't do this with a tertiary alcohol. You can only do it with primary, secondary alcohol. You could do it with methanol as well, but you cannot have a tertiary center there. So what we're trying to do, what we're trying to accomplish is we want to replace the OH with the cyano group. Okay? Now before we do that, let's just think about what's happening. If you look at the priorities of these groups in terms of the Kahn-Ingold-Prelog system, this would be priority number 1, this would be 2, the methyls 3, hydrogens 4. So this is going clockwise. Okay, 1, 2, 3, we're going clockwise. So this alcohol is R in absolute stereochemistry. If you come over here, you might notice it's been replaced by a cyano group. That'd be priority number 1 as well. This is still 2, methyl still 3. Now I have to invert that. But here we're going to the S in the enantiomer. So that should tell you that we're doing an SN2 reaction. We might as well sketch that in. We're doing an SN2. And the final step is simply hydrolysis of the cyano group to a carboxylic acid. We won't go through that mechanism. Okay, if we have time at the end of organic chemistry, we'll do that. So we go from cyano to a carboxylic acid. So how would you go about this? In other words, what can we do in order to conduct this? We have to keep our eyes on this reaction above. The first thing we want to do is that we need tosyl chloride. And rather than drawing that whole structure out, let me just write TOSCl. Okay? Now this isn't the official way of abbreviating it, but this is the way we traditionally do it in a sophomore organic chemistry. And what else do we have here? We have pyridine. So I can just write the word pyridine. Some people just write the letters PYR. I've seen people just write the letters PY. Okay. Don't want to get too lazy. But by virtue of placing tosyl chloride in the presence of an alcohol, in this case a secondary alcohol, we're going to produce what's known as an O-tosylate. Okay? And the reason we're doing that is we're trying to convert that group into a good leaving group. The hydroxyl group is going to be a good leaving group. Alright. Bear with me. Alright, so before you formerly had a proton, okay, you now have a tosyl group. Okay? So O-tos. Nothing's changed about the stereochemistry about this chirality center. Okay? It's still R in absolute stereochemistry. And the byproduct, of course, would be this. Okay? Pyridinium hydrochloride. We don't need to show that. Okay. We're nearly done. I'm going to draw an arrow that goes straight to B. Okay? Because we just need a source of cyano ions. Okay? You need something ionic though, preferentially. So how about we use sodium cyanide? Okay? And also you would probably prefer a solvent that was a polar aprotic to support that. Those are better for SN2 processes. You can just write that in. Polar aprotic solvent. Okay. And that's good for SN2. Right? Now, if you're wondering what exactly happened here, let's just answer that question this way. Sodium cyanide is a salt, and when you place it in a polar solvent, it's going to dissociate into its respective ions. Okay, in this case we would have a sodium cation, which is a spectator, and we have a cyanoanion, or cyanide anion. And it's going to do a backside approach. It'd be, it would come behind that oxygen, but I'm just showing a curved arrow here, and then that would break off. But we get inversion. Sometimes they call this the Walden inversion. Okay, we write that down. Walden inversion. And there's a Walden inversion cycle that we looked at in an earlier chapter. Okay? So that's what goes on here. This is the way to convert poor leaving groups into good leaving groups. You conduct an SN2 reaction, therefore you end up with the desired species. And notice in this case we go from R to S in absolute stereochemistry. Alright, a little bit more. Back in chapter 8 you also learned that alcohols can be dehydrated to form alkenes. So this was called dehydration of alcohols to yield alkenes. This is something you learned back in chapter 8. Now, as it turns out, this is a pretty good reaction, okay? Because first off, you're beginning with tertiary alcohol, sulfuric acid, water, tetrahydrofuran, you have to heat it up. 50 degrees is pretty hot, and you get a pretty good yield, 91%. But this is a very strong acid. These conditions are quite harsh, and while that yield's pretty good, that's an exception. Most of the time you don't get yields that are this good, okay? And primarily because these conditions are so harsh. Now, that being said though, let's just remind ourselves of how this works, okay? And the way I'm going to do that is by reminding you of the basic aspect associated with dehydration. What you want to do is you want to find the carbon that bears the OH, okay? And we're going to label that alpha. Okay, there's your alpha carbon. And the adjacent carbons we're going to label beta. Okay, so technically this is a beta carbon also. I'll call it beta prime. So what happens? You end up producing a double bond between alpha and beta. Okay, alpha and beta. And this is called the Zaitsev alkene. And the Zaitsev alkene would be the most substituted alkene, and therefore it's the most stable. You may get a little bit between double bond between alpha and beta prime, but certainly not very much, as you can tell by that percentage. So this is something you learned back in chapter 8 in terms of reactions of alcohols. So what we want to do though is go a little bit further than that, right? Let's go ahead and do one more practice problem just so we can remind ourselves how this overall system works. And then after that, okay, we'll look at a different process for dehydrating alcohols. Okay. Now, folks, this is a strong acid. Again, we have a solvent here, and the temperature is a little lower, but that just means we might have a little bit longer reaction time. So what you need to do is you need to locate your alpha carbon, and that's always the carbon that bears the OH. Then you need to locate the beta carbons. This is beta, and this is beta, and this is also beta, but because it's part of an ethyl group, I'm going to call that beta prime. Okay? Now, we can anticipate, two different alkenes here. One where we produce a double bond between alpha and beta, and one where we produce a double bond between alpha and beta prime. Okay? I think the best way to sketch this one out is, okay, maybe not, just to draw a zigzag structure. Now bear in mind, you're not losing, okay, you're not losing any carbons. You're only losing water. You're losing an OH and a proton from the beta carbon when you do this. So let's go ahead and figure out one of the structures here. Let's draw one with a double bond between alpha and beta. Okay? Alpha and beta. So there's the beta carbon, and it's going to be doubly bonded to the alpha carbon, and the alpha carbon has a methyl group on it. It also has an ethyl group on it. Alright, so there's one of your products. See how we did that? Let me label the alpha and the beta. So this was alpha, and this is beta. Now let's jump over here and do the same thing on the other side. Okay? Only now we're going to have a double bond between alpha and beta prime. So here's a methyl. There's that carbon it's attached to. Okay? There's the other methyl group. And now we have a double bond, carbon, and we have a methyl group there. Okay? So let's label the alpha and the beta there respectively as well. So this is alpha, and this is beta prime. Okay? Alright, so there are your two constitutional isomers that you get from dehydration. But it said which one's the major, which one's the major and which one's the minor. Major and minor. Okay. The major one's the more substituted one. That's called the diacetylalkene. I alluded to that on page 96. This is major. You get more of it because it's more substituted, more stable, and obviously this would be the minor. Okay? And if you remember anything about substitution, this species here has two R groups attached to the double bond, so it's disubstituted. This has 1, 2, 3 R groups attached to the double bond, so therefore it's trisubstituted. The greater level of substitution, the more stable the recipient alkene. So this is something you had back in chapter 8. Now, folks, these conditions are pretty harsh. Is there something else that we can do to get better yields and have maybe a better performance? And the answer is yes, there is. Here we have another example of a tertiary alcohol. This is 1-methylcyclohexanol. Folks, this is called phosphoryl chloride, POCl3. Okay, there's its structure. And kind of like tosyl chloride, it's going to result in the formation of a really good leaving group. But it works with tertiaries. So we'll have to look at that mechanism, pretty closely. So as before, nothing's really changed in terms of our designation of the nuclei. The carbon that bears the leaving group is OH. Okay. We're going to label alpha. And the adjacent carbon beta, beta, beta prime. And so you can tell at a glance that most of our alkene, our cycloalkene, was a result of the dehydration happening between alpha and beta. And also we have this particular acid that I'll talk about in the next step, left over as a byproduct, and pyridinium hydrochloride, our good friend. Now the reason you did this reaction, okay, was to make this particular alkene, okay? That's why you did it. Alright. Now, let's provide a set of curved arrows to get a feel for how this works, okay? I want to get a feel for how this works. Okay, now this case, we have a very similar alcohol. Okay, this is the cyclohexanol. It's a secondary alcohol. And here's our phosphoryl chloride. Okay. So what's step one? Step one is the oxygen is going to behave as a nucleophile towards the phosphorus. And phosphorus is very electropositive because it has, guess what, 3 chlorines attached as well as a highly electronegative oxygen. So any one of the 3 chlorides can break away. Okay? And so now what do you have? What you have here is a situation whereby you've established a really good leaving group. Okay? Okay. Now this reaction can actually proceed one of 2 ways. One, because it's secondary, this bond could break and you'd have a carbocation, and you'd have a subsequent loss of a proton from here. But probably what happens the greater percentage of the time is the following. Okay? Let me just show you. Look, let's go ahead and sketch in those two hydrogens on that adjacent methylene. All right, and just so you can get a better image of what's happening, let me sketch that proton in as well. Remember pyridine? Okay. Pyridine not only functions as a solvent, but it functions as a Lewis base. Now these protons that you're looking at, they're very accessible. It's very easy to get at them. So the lone pair on the nitrogen can come in here, pick up either of these two protons. This pair of electrons collapses between the alpha and the beta carbon, and this bond here will break because guess what? This is now a good leaving group, LG. And so the net result here is you end up with cyclohexene. So this would be the prominent mechanism if you had a secondary alcohol. If you had a tertiary alcohol, it would be more likely that the leaving group would break off first, and then you have double bond formation. So this particular process here, okay, is called E2. It's elimination bimolecular. But it's a way of converting alcohols into alkenes, or more specifically a cycloalkene. Now let's give the next problem a try. Okay? This is a pretty tough problem because they have a lot of different elements associated with it. So what products would you expect in the dehydration of the following alcohol? Okay? Alright, here we have phosphorus chloride, we have pyridine. Alright? Now the stereochemistry is very explicit here. Okay? In other words, you can see that the OH group and the methyl group are trans one another, and that matters. Okay? That matters. So, cutting to the chase, the secondary alcohol is going to be converted into a good leaving group. Okay, let me write this down. But if we go back to the bottom of page 97, we see what's going to happen. Right? Now, what do you mean we see what's going to happen? Let me sketch the letter alpha here and remind ourselves that the adjacent carbons are beta. Okay? Now, are these beta carbons identical? No, they're not. This beta carbon here has a hydrogen and a methyl, whereas this one over here is a methylene. It's a methylene. So I'm going to call that one beta prime. So they're different. Okay. Now, you may remember the terms anti-periplanar. Anti-periplanar. Once this gets converted into a good leaving group, it will leave, but it will happen in an anti-periplanar fashion. So the proton that gets abstracted by pyridine is the one that's anti-periplanar to the hydroxy group once it's been converted into a good leaving group. So you're only going to establish a double bond there. Okay? You're only going to establish a double bond there. So let me sketch that with you. Alright? So, no double bond. Okay? No double bond between this alpha and that beta. But you do get a double bond here. Okay? Because of the anti-periplanar relationship between these two groups. Alright? Okay. Folks, let's go ahead and finish up this material by talking about how to convert alcohols into esters. This is also something that we had intended on doing in the lab. But the way you do that is by first beginning, there's more than one way. You start with a carboxylic acid, you take an alcohol with an acid catalyst, and suddenly it becomes an ester. An alternative approach to that would be to convert the carboxylic acid into an acid chloride using thionyl chloride in the presence of pyridine, and then reacting that with an alcohol and pyridine. Either route you take, you get the same ester. Now, that's a lot said in one sentence, but here's how this would work. Notice here we have benzoic acid, we have ethanol, and we have an acid catalyst. What's going to happen here is we're going to replace, okay, that proton with this. Actually, we're going to replace this whole group, the OH group, entirely with this. So it's become really easy to understand once you see how this works in an overall sense. So where you formerly have an OH group, okay, so you formerly had an OH group, you've now replaced that with a, in this case, an ethoxy group, okay, and that came from the alcohol. So this is your ester. This is your ester. And in case you're wondering about the byproducts of which you're not responsible for, here you would have water as a byproduct. Okay, this is called a Fischer esterification reaction. Oops, did y'all see that? Yeah, this is called a Fischer esterification reaction. Now on the bottom, this is different. Notice here we have a carboxylic acid, but on the bottom we have an acid chloride. Okay. You could convert that to this by using thionyl chloride, okay, in the presence of pyridine. Then you conduct this essentially the same reaction. You add alcohol, in this case ethanol, to the acid chloride, and look what you get. You get the same results that you had above. So these are two different approaches, but they result in giving the same product. So I wanted to demonstrate it that way so you can see, okay, just how these processes work. And of course the byproduct here would be pyridinium hydrochloride. Okay, so let me just write the word salt as your byproduct. So that's how you convert carboxylic acids into esters or acid chlorides into esters using this process. All right. Okay. Just about done. Let's go to page 99. Folks, this deals with the oxidation of alcohols. And I'm going to introduce to you something you've never heard about before called the Dez-Martin pyridinane. Now this is the compound here called Dez-Martin pyridinane, named after the chemist who came up with it. You'll see in a moment that Dez-Martin converts primary alcohols into aldehydes very cleanly with very high yields, and similarly it converts secondary alcohols into ketones, extremely high yields. Okay, and if you want to see a detailed mechanism, go to McMurray for that. I don't expect you to understand this mechanism. It's just really beyond what we need to know for software organic. But this iodine here is a hypervalent iodine. Normally you're just used to seeing one bond iodine. How many do you see there? 1, 2, 3, 4, 5. Okay, that's 10 electrons around that iodine, so it's hypervalent. Furthermore, we've abbreviated, folks, the letter AC, or more specifically OAC, is that. So if I would try to draw this whole thing here, it just ends up being a very cluttered looking compound. So here's how it works. And this is what I want you to know. Folks, if you see Dez-Martin pyridinane, and typically it is conducted in dichloromethane, all you have to do is recognize the order of the alcohol. In this case, we have a primary alcohol. And what did we say? Primary alcohols yield aldehydes. So we're going to oxidize this position. So 1, 2, 3, 4 carbon chain. Okay. And now now that's going to be an aldehyde. Okay, if you want to, I'm going to go ahead and sketch that hydrogen in. It's that simple. So this is an oxidation. Look at the next example. This is a secondary alcohol, right? Okay, secondary alcohol. What are you doing? You're exposing it to the Dez-Martin periodinane, this reagent. And what did we say? Secondary alcohols get converted into ketones. So we have a 1, 2, 3, 4, 5 carbon chain this time. And the oxidation occurs here at carbon 2. So now we have a ketone. So primary alcohols do what? They give us aldehydes. Secondary alcohols do what? They give us ketones. Okay? So what's your job? Your job would be simply to tell me what the product would be in the event you were to oxidize either a primary alcohol or a secondary alcohol. And bear in mind, you can't oxidize tertiary alcohols, okay? Only primary and secondary. This is a relatively new reagent, very expensive, but it's really good. I mean, the yields here are nearly quantitative, meaning that you get practically 100% yields. Many moons ago, that wasn't the case. Okay, in those many moons ago, I'm kind of dating myself. I've done this. The Jones reagent can also be used to oxidize things. Okay, and I'll explain how this works. With Jones reagent, folks, this is a very harsh. Okay, very harsh oxidant. So it's going to oxidize big time, whatever it is you have. So, as opposed to the Dez-Martin, with the Jones reagent, primary alcohol has been oxidized all the way to carboxylic acids, whereas secondaries will oxidize to ketones, which is really the same as Dez-Martin. So this is different than Dez-Martin, this is the same. The drawback is both of them give you very poor yields, and furthermore, the reagent itself is carcinogenic. So what does Jones reagent look like? Jones reagent looks like this. Folks, this is chromium 6 oxide, okay, or hexavalent chromium, is a very, very toxic heavy metal. And the pH has been lowered dramatically by adding acid, and it's also conducted in solvent. Alternatively, you can use sodium dichromate in the presence of acetic acid and heat. But any of those give you chromic acid, okay, chromic acid, which is a very harsh acid that can oxidize things. So let's go to our last page just to see how that works. So did you ever think we'd get to page 100? Here we are. And we'll stop after this, and it'll be the end of chapter 17. So think back to what we just said about Jones reagent. Okay, we have it in different forms. This is a chromium 6 oxide and acid and acetone. This is what kind of compound? This is a primary alcohol. But unlike Dez-Martin, we're not just going to oxidize between here and here. We're going to fully oxidize the species. So let's count the carbons. 1, 2, 3, 4. So we're going to oxidize that alcohol to a carboxylic acid. Okay? And the yields probably aren't that good, but rest assured that's your organic product. Here we have a secondary alcohol, and now we're generating chromic acid by adding sodium dichromate in the presence of acetic acid, some water to dissolve it all up, and we're heating. Let's count the carbons. 1, 2, 3, 4, 5. So we have a 5-carbon chain. Right? And at the 2 position, we're oxidizing this to a ketone. So let's think about the net results here when we use Jones reagent. Okay, we're using Jones conditions. A primary alcohol gives you what? A carboxylic acid. And a secondary alcohol gives you what? A ketone. So this was different in its result than Dez-Martin. This is the same as Dez-Martin. Okay, folks, that's the end of chapter 17.